All right, so today and tomorrow we're going to look at section 4.2, okay, which is all sketching. Okay, we're not going to be solving really too many in-depth kind of equations with this stuff, mostly graphing. All right, so just a reminder that if the numerator and denominator have a common factor, you can set that factor equal to 0. You don't get an asymptote there. What happens when you get a numerator and denominator with a common factor? Instead of an asymptote, you get a hole. Okay? So keep that in mind. You get a very small hole. And it's something that you can't notice with the calculator. Okay? No matter how much you zoom in, you're never going to see a hole on the calculator. So let's just try graphing a couple things that have holes, just so we can remember what they look like. And just kind of see what happens. All right, let's graph that. X minus 1 divided by x minus 1. Now, when you divide two things that are the same, what do you get? And which whole number in particular? If you divide two things that are the same. Like 8 divided by 8 or 2 divided by 2. What did you say, Colin? 1. 1. So basically, you're dividing two things that are the same here. So this is going to look like the graph y equals 1. But there's going to be a hole in it. What value of x are you not allowed to use here? 1. 1. If you plug 1 in, you would divide by 0. All right, so let's take a look at it. Let's see what it looks like. X minus 1 divided by x.
Does it have to be in parentheses? Can you do x minus 1 divided by x minus 1?
I would put it in parentheses. You can try it without and see if you get the same picture I do. Okay, it looks like a horizontal line. But is that really connected? What do you think, AJ? Well, what did we say?
Well, if it goes opposite in both directions, then it's not connected. What
did we say, though, about a value of x you can't use? 1. And we said that what's going to happen at 1? You're going to have a small hole. So no. Even though, again, the calculator can't show it, right?
What if you zoom?
Even if you zoom in, you're not going to be able to notice it with the calculator. No matter how much you zoom in. You can zoom in like 15 times.
The line goes all the way up to 1, then it gaps, and
yep.
It goes.
Yep. So what it really looks like, if you want to exaggerate it, is it kind of looks like, all right, like this. Here's your line. At 1, there's a hole, and then it keeps going. That's what it really looks like. Okay. You won't notice it with the calculator, though. Again, you can zoom in
so you can notice
as much as you want. Yep. Do you see it?
Yeah, you can see it with this one.
Oh, you can see it?
Yeah, there's a little space out one.
Let me see.
X and the y meant to 2 or -2.
Let me zoom in. Let's see. Usually when I zoom in, I can't see it. Let's zoom in. All right, so I'm zooming in.
No. Yeah, you can see it on this one.
Maybe maybe different model. Let me zoom in again. So if I zoom in again, I can't see it on mine. But I guess maybe it depends on the calculator. Yeah. In general, though, you wouldn't know that it's there, so you just have to look at your equation. That's how you can tell. Okay. All right, so any question on that? Okay, so that's a hole. Now, if I changed it to that, do the numerator and denominator have a common factor now? No. They're different factors. So, you're still going to have a problem at 1 because you can't divide by 0, but instead of having a hole, this time you're going to have a vertical asymptote. Let me show you what that looks like. Okay, so just by changing one thing, it kind of starts looking the same, but then it looks very different at 1 now. You have a vertical asymptote. Bless you. Okay, so you could change pretty much anything here. Okay? If you made that a minus 2, right, then you'd have the same thing. You would have a vertical asymptote, okay? Because now the numerator and denominator are not common factors. So it starts off looking the same, but then look what happens near 1. Okay, vertical asymptote. Okay, so common factor in the top and bottom, whole. No common factor, asymptote. Okay, what would happen, I'm not going to graph it, but what would happen on this one? Would you have a whole at 1 or an asymptote?
Asymptote. No, you have a whole.
Well, do the top and bottom have a common factor? Yeah. The top is basically this. It's 2 copies of x minus 1 over x minus 1. So basically what's going to happen is these cancel out, and it's going to look like a graph with a slope of 1 and a y-intercept at -1. So that's what it would look like. But remember, there's a hole. Just because these cancel out doesn't mean the hole's gone. The hole is still there. Okay? And you can't see it from the, well, usually you can't see it from the graph. I'll have to take a look at that after. I'd like to see why yours can show it and mine can't. All right, so that hole, that's what we call a removable discontinuity. It's such a small gap that if it's that small, we call it a removable discontinuity. So basically it's like if we could just fill that hole in, if we could just fix that one little spot, then it would be continuous. If all you have to do is fix one little spot, that's a removable discontinuity. Okay, a vertical asymptote is not removable. That's a much bigger problem, right? So if you have a graph that does this, it's not like you can just put in one little dot and make these two things connect. Okay, a vertical asymptote, it's totally messed up. It's not connected at all. It's not even close to being connected. But this one was very close. It just had a small hole. Okay, so the proper name for a hole, it's called a removable discontinuity. Any question on that? So that's the name for a hole, removable discontinuity. All right. So suppose you had a rational function. Okay, when we do a problem, it's going to look like that. Just going to be a polynomial on the top and on the bottom. I'm always going to write it highest to lowest exponent. I'll always put the constant right at the end. And that's all that is. Right, so it might be something like 3x cubed plus 9x squared plus 8x plus 6. Okay, something like that. Okay, so last week we talked about the EBM, okay, the end behavior model. Does anybody remember which term there? Let's just focus on the top. Which term in the one with the highest exponent, right? So if we were looking at a problem, there's the EBM in the top. There's the EBM in the bottom. Same thing here. That's the EBM for the numerator. That's the EBM for the denominator. Now, what do you think you would do with each of those if you wanted the EBM for the whole thing? What would you do with the one in the top and the one in the bottom? Divide them. Exactly. Right. So if you want to find what's called the EBM for this whole thing, find the highest degree term in the top, find the highest degree term in the bottom, and divide them. So remember that the EBM means it predicts what the function is going to look like if you zoom out. The EBM doesn't predict all the small details. If you want to know all the little kind of twists and turns the graph is going to take, the EBM is not what you want. EBM is big picture. You zoom way out, this is what this thing is going to look like. It's kind of like if you were looking at Earth from outer space. That's the EBM, big picture. Okay. If you're looking at Earth from outer space, you're not going to see what somebody's writing on their sidewalk. Right? If you want to know the little details like that, then that's where you're going to look at all the smaller stuff, like the -1s and +1s. Now, when you divide two things that have the same base, anybody remember what you do with your exponents?
Subtract them.
You subtract them. It's like if you had 2 to the 5th over 2 to the 1st, that's 2 to the 4th, which is 5 minus 1. So same thing here. Subtract your exponents. And the number in front of x in the top and in the bottom, those will be actual numbers. Maybe it'll be like 3 and a 2 or something. Okay, so find the EBM in the top, find the EBM in the bottom, divide them. Okay, so let's try the example that I kept jumping to, and then we'll do it with some actual numbers. All right, so first one. I've kind of already circled the EBM here, so we'll just write it down. The highest degree term in the top is 2x squared. The highest degree term in the bottom is 3x cubed. And now we simplify it. So when you simplify it, you should only have x's in the top or the bottom when you're done. If you have x's in both the top and the bottom, you haven't finished simplifying yet. Okay. And if you were to subtract the way it is, 2 minus 3 would give you what kind of number?
Negative.
It'd be a negative. We don't want to write our answer with negative numbers. Okay, so think of it this way. Okay, you have 2 copies of x in the top. You have 3 copies of x in the bottom. Anywhere you have the same thing in the top and the bottom, you can cancel it. That copy's gone. That copy's gone. So, bless you. The x that I have left, where is it? Is it in the top or the bottom?
The bottom.
The bottom. That basically means it's negative. Anytime you leave something in the bottom, that means that the exponent, if you had just subtracted, would have been a negative. Right. That's how I'd always like you to do it. Rather than write it, you could do this, but I would rather you do that. Okay. Numerically, same thing. It's just, trust me, you're going to find this one easier to work with. And that's it. That's your end behavior model. Any question on that? And now the end behavior model is used to give you the horizontal asymptote. To get your horizontal asymptote, look at your end behavior model and let x get really big. All this stuff of like minusing 1 and plus 1, those are just little details that if x is approaching a huge number, like if x is 1,000,000, and you square it and then double it, or you take 1,000,000, square it, double it, and subtract 1, there's not really a big difference. Okay, subtracting 1 from a number that big, it almost doesn't even matter. Okay. So just look at your EBM and let x get really, really big. What happens to this fraction as x gets really big?
It's closer to 0.
It gets closer to 0. Okay? If x was 10, you'd have 2 divided by 30. If x was 100, you'd have 2 divided by 300. Okay? If x is 1,000,000, you'd have 2 divided by 3,000,000. It's getting smaller and smaller, okay? Approaching 0. Will it ever reach 0? No. It can't reach 0 because even if you take 2 and divide by 1,000,000,000, it's still not 0. Very, very small, but not 0. So any question on how we found the EBM or the horizontal asymptote? Let's try this one. Wyatt, what's the highest degree term in the top?
2x to the 4th.
Good. 2x to the 4th. So we got that. And Colleen, do you see what the highest degree term in the bottom is?
3x to the 4th.
Yep. 3x to the 4th. And now when I divide them, about Curtis, how many x's do I have in the top? How many copies of x? 4? How many in the bottom?
4, so it's going to cancel out.
Same amount in the top and the bottom. There's your end behavior asymptote. And behavior model. Any question on the EDM? Now, what do we do to x to find the horizontal asymptote? We let x, what, Colin?
Get as big as possible.
Let x get as big as possible, right? Let it get really big. So, look at the fraction 2/3. What happens if you let x get really, really big in that fraction I just circled? What does that fraction get close to? Any thought? Josh?
0.6.
Keep your answer as a fraction, if you're going to give me a fraction.
Wouldn't it just be 2/3?
It would just be 2/3. There is no spot for x. So if all your x's cancel out, your horizontal asymptote is just whatever the EBM was. They're the same thing. So let x get really, really big. Well, it's 2/3. So anytime you have the same degree in the top and the bottom, all the x's are going to cancel out. And you're going to get a horizontal asymptote at a number that's not 0. Anytime you have x's and the degree in the bottom is bigger than the top, that's a degree 3, that's a degree 2, you're always going to be left with an x in the bottom. And that's going to be an asymptote at 0. Always. So anytime the degree in the bottom is bigger, horizontal asymptote always at 0. Anytime the degrees are equal, well, just divide the two numbers that are in front of the x's, and that's your answer. Okay, so both of these are cases where the degree of the numerator was either less than, like this one, degree of the numerator was less than, or equal. Okay, the second one I did with you guys was equal. And that's the kind of graph we're going to look at today. Tomorrow we'll look at when the degree of the numerator is bigger than the denominator. But not today. Right, so I'm going to give you kind of some general suggestions, okay, on how to graph it. Not all of these suggestions apply to every problem, because every problem is a little different. One thing that is helpful is to find your intercepts, if they exist. If you had a graph like this, that's a graph that never crosses the x or y axis. So you're not always going to have intercepts. But if you do, it's a good idea to find them. Okay, that's helpful. To find your x-intercept, plug 0 in for y. To find your y-intercept, plug 0 in for x. Okay, the next thing that's going to be helpful when you're making a graph is to find your vertical asymptotes. Vertical asymptotes are where the denominator equals 0. Okay, we said that yesterday. Okay, the next thing you want to find is your horizontal asymptote. Okay, how do you do that? That's what we just did in the last two problems. Find the EBM, and like Colin said, let x get as big as you can. Let it get really big. And whatever the result is, that's your horizontal asymptote. Just a reminder, vertical asymptote, what letter does that always start out with? Is that x equals or y equals? Well, Dave?
X equals?
Remember? Yeah, vertical asymptote, that's x equals. Horizontal, y equals. Don't mix those up.
So it's backwards?
What's that? Yeah, it's not like you would think, oh, x-axis is horizontal, yeah. Horizontal is always y equals. And then once you find the vertical asymptote, like let's say your vertical asymptote was at 2. We're going to use the graphing calculator to check in the table what happens close to 2. You can't check 2. 2 is going to give you an error. That would be like divide by 0. But we'll check something very close to 2, like 1.99, and see what happens. And then we also want to check something very close to 2, but on the other side. So 1.99 is a little smaller, 2.01 is just a little bigger. Okay, and we have to do that for every vertical asymptote. So we will check what happens as you get very, very close to it. And then the last thing, you can always double check on the calculator and make sure things look right. Okay, so I have three sketches, and we'll see how many we get through. I think once you do the first two, that covers everything that can happen. The third one would be an extra if we had time. Okay, so I'll start out with one where the numerator is less. The second one I'll do is where the numerator is equal. So I'll do one of each. And you don't have to do these steps in this order. Like if you want to find the vertical asymptote before the horizontal, that's fine. You have to find both. Do them in whatever order you want. Okay. So let's see if we can sketch a picture of that graph. What I like to do out of all the steps I listed, I like to find the asymptotes first. Vertical and horizontal, doesn't matter what order. Let's start with the horizontal. Okay, to find the horizontals, you're going to find the EBM first, and then let x get really big. So Ian, what's the highest degree term in the top?
In the top?
Yeah. Yep, and in the bottom? X squared. And if you simplify that, what are you left with?
1 over x.
Perfect, 1 over x. Now, let x get really big. Ezekiel, what happens to that fraction as x approaches infinity?
It cannot pass through 0.
Right, it's going to approach what number?
0.
0. If x is 10, you get 1/10. If x is 1,000, you get 1/1000th. So it's very, very small, but it's never going to hit 0. Okay. So first thing I'm going to do is I'm going to put a dotted line, horizontal, at 0. Let's put that right there. All right, horizontal asymptote. What other kind of asymptotes can we find besides the horizontal? The vertical. Okay, let's go back and look. vertical asymptotes. That's where you set the denominator equal to 0. Okay. So let's take our denominator, x squared minus x minus 6, set it equal to 0. Okay, when you solve a quadratic, what's one option for solving it?
Factoring.
Factoring, which is going to work here. If you couldn't factor it, what would you have to do?
Quadratic.
You could use the quadratic equation. Yep, quadratic formula. All right, so we're going to need an x and an x. Two numbers that multiply to give me 6 and subtract to give me 1. Or negative 1, same thing. Yep, we're going to need the 3 and the 2. And I would do it as a minus 3 plus 2. So x times x is x squared, minus 3x plus 2x is plus minus 1x. Any question on that factoring? Right. Notice the two factors we have in the bottom, x plus 2, x minus 3. The factor in the top is x minus 1. Any common factors here? No, so you're not going to get any holes in this graph. But you are going to have two vertical asymptotes. Caitlin, what value would I plug in for x to make the first factor 0? Yep. And how about the second factor? Positive 3. Okay, let's sketch those. Negative 2, positive 3. All right, so negative 2, positive 3. Right, so my asymptotes kind of give me boundary lines. They give me sections that I'm going to put the graph in, and my graph is never going to cross over those boundary lines. Let's see if we have intercepts. Okay, let's start with the x-intercept. So that means you set y equal to 0. Okay, well, that's y right there. So if you set what I just circled, if you put a 0 in for that, you'd have 0 equals that fraction. What's the only way that a fraction can ever equal 0? Ian? If the top is 0. It doesn't matter what the bottom is. So if the top equals 0, then the entire fraction equals 0. Any question on that? Okay, so what would make the top 0? 1. That's my x-intercept. This is going to cross the x-axis at 1. My y-intercept. This time, you don't plug in a 0 for y, you plug in a 0 for x. So what's 0 minus 1? Negative 1 over 0 squared minus 0 minus 6. Just negative 6. So this graph is going to cross the y-axis at 1/6. Okay, so now the last thing we're going to do is check what's happening near negative 2 and positive 3. Okay, and I'm going to use the calculator, and this is where I showed you how to set up your table. Okay, so if you haven't typed in your equation, that's step 1. X minus 1 divided by x squared minus x minus 6. Now, if you try negative 2, we get an error, because that's divided by 0. If you try 3, we get an error. So what we did is we just confirmed that those are the correct asymptotes. The factoring was pretty straightforward, so I think we already knew that. Let's try a number very close to 3. Can somebody give me a number that's extremely close to 3? Even closer. 2.99. So when I'm at 2.99, I'm way down at negative 40. If I go even closer, negative 4,000. So what's happening is as I get very close to 3, my graph is going way down. So there's negative 4,000 right there. Close enough. All right. I also want to check what's happening just on the other side of 3. Someone give me a number that's just a little bigger than 3. 3.01, sure. So now we're going to check what happens just after that green vertical line. All right. So if you go just after it, you're way up at 40. Okay. If you go even closer, you're up at 40,000. And notice it just says 3 because eventually it runs out of room to put the decimals. But just after 3, your graph is way, way up high. Way up there.
But what does it do if you just say 3?
Well, yeah, if you put in 3, it's going to say error.
Yeah.
Okay. Now let's try this one. Negative 2. Can someone give me a number very close to negative 2?
Negative 1.99.
Yep. So negative 1.99. Okay. So that's just to the right of negative 2. Right? Negative 1.99. You're way, way up. So way up here. Now, let's try a number just after negative 2. Just after negative 2, to the left of it, you're way down. Usually what ends up happening is one side of the asymptote, you're way up high, the other side, way down low. Okay, you should always double check, but that's usually what happens. Now, what would be one other good value to check for, like, what's happening over here? What would be a good x value to the left side of my graph?
Anything bigger than negative 2?
Anything what?
Anything, well, yeah, anything less than negative 2.
So yeah, why don't we check like negative 10, just to kind of see where am I right on the edge of my graph. Negative 10, we're at negative 0.1. And we should have already known we were going to be close to 0 because that's the horizontal asymptote. It's going to get very close to 0. And same thing here. All right, so let's start with the lower left section. You've got a line that's very close. As you move towards 0, it's going to start to move away from it. Same thing here. You have a line, it's very close. As you start to head up, it's going to start to move away from it. And those two need to connect. And the only way they can really connect is some kind of curve like that. Pretty much the exact same thing is going to happen in the upper right. You have to be very, very close. You're going to head down, but you can't cross the horizontal, so all of a sudden it's going to have to start to curve. Okay, like that. Where exactly does it curve, or how sharp of a curve is it? That I don't care if you get that part exact. Just the general idea. Now in the middle. Well, in the middle, we have to be getting closer and closer to the asymptote on the right as you head down, and the asymptote on the left as you head up, and we're going to have to go right through those two dots in the middle. So the only way it can look is something like this. And that's pretty typical of what these graphs look like. Let's do zoom 6 and see how we did. So there's the section in the lower left. There's the middle. So you can see, I think their graphs, the turns are much sharper. This almost looks like an L shape, right? Where mine is a little more smooth curve. That's fine. Okay, as long as you have the general idea, that's all you need. Okay, so any questions? questions on that? It's kind of different. It's the first one we've ever done that's like that. Any questions on it? Okay, graphing these kind of things, well, two things happen. One, you start to realize that they always look like that, so you know what you're looking for. And two, it just takes a little bit of practice to get your sketch. Okay, we'll try one more. Okay, so this one, the degree in the top was a 1, degree in the bottom was a 2. Degree in the top was smaller. Let's try this one. What's the degree in the top of this one? What's the degree in the top?
3x squared.
And the degree would be?
2.
2. Degree in the bottom?
2.
2. This is a case where they're equal. So let's start with our horizontal. What do you find that helps you to get the horizontal? We don't find the horizontal right away. We find the what? Yep, we find the EBM, the end behavior model. And Josh, what's the term in the top that's going to control everything?
3x squared.
3x squared. And the term in the bottom?
2x squared.
2x squared. So I'm left with 3 over 2.
Yeah.
Okay, my EBM is 3 halves. So now, looking at that fraction, as x gets bigger and bigger in this fraction, what does that fraction approach? 3 over 2. Okay, we did one like that before. There is no x. So if there is no x, there's nothing to do. And now 3 over 2, what is that as a decimal? Because when you're graphing, that's decimal is a little easier.
1.5.
1.5. So put a horizontal at 1.5. Okay, right about close enough. Okay, vertical asymptotes. Can someone remind me, how do you find your vertical asymptotes? Yep, you do something with the denominator. What do you set it equal to? Set it equal to 0. And Josie already started to tell us how we solve it. What did you say? Factor it. This one isn't as bad to factor. This is just a GCF. So just pull out an x. And what would you be left with?
X squared
So
2x
an x and a 2.
minus 5.
Minus 5. Okay, Jesus. Now, set each factor equal to 0. So set the first one equal to 0. Second one equal to 0. What do you get when you solve the first one and get x by itself? 0. It's already solved. What do you get when you solve the second one? 5 over 2. And let's do that as a decimal. What's half of 5?
2.5.
2.5. Again, normally I don't use the decimal, but for graphing it's easier. Right. So 0, 2.5. Right. So you can see this is kind of turning out just like the last one. You've got the 3 sections again. Now, let's just figure out what's happening in each section. Okay. If you don't want to use a calculator, you don't have to, but I think using the table makes it a lot faster. So we're going to type in 3x squared plus x minus 4. 3x squared plus x minus 4, and I would use parentheses just to make sure it does it okay. I'm going to divide by 2x squared minus 5x. All right. If you have values already in there from before, you can just ignore them. We don't need them. Okay, where's my first vertical asymptote, Kelvin?
The first vertical asymptote.
Yep.
Is 0.
0. Can you give me a number a little smaller than 0?
0.01.
That's bigger.
Oh, negative 0.01.
Yep, negative 0.01 or 0.001. So if we go just to the left of 0, we are way down. Now I'll type in the other number he said, just to the right of 0.
0.01.
0.01, way up. All right, now my next asymptote was 2.5. What's a number just a little smaller than 2.5?
2.4.
A little closer?
2.45. 2.49.
Sure, let's go within 100th. Yeah. So if you get very close, but you're still a little smaller, graph is way down. All right. To the right, a little bigger than 2.5.
2.6.
2.6.
Let's go even closer.
2.5.
2.01.
2.01. Little bigger than 2.5.
2.51.
Yeah, 2.5.
I thought you were saying like a little bit over 2.
So now, if you type that in, you're way up at 300 something. Way up here. So now remember what's going to happen in each section. This has to come up. Stay very close. Okay, curve away. Other section. This is going to come down and curve. The only thing I'm not 100% sure what's going to happen in the middle. So what would be an x value I could try in the middle? Just to get maybe one more point. Yeah, let's plug in 1. When x is 1, that's where you cross the axis. Right there. So what's going to happen is something like this. It's going to stay very close. Start to move away from it. It's okay that it crosses the horizontal asymptote because it's not crossing it far away from the origin. Okay? It's as you move far away, it doesn't cross. Not near the middle. So it's going to come down and then kind of go like that. So in here, it's very steep. So I think when you try to graph it on the calculator is not going to be able to sketch this. At least it's probably just going to stop and cut it off. Okay, let's look at it. Okay, I don't think it'll have any problem with the right section. But see in the middle how it just looks like it stops? It's because it's getting so steep in that section it can't sketch it. But that's what it should look like. Any question on that one? So general rule here, you kind of get these L-shaped curves in the upper left and or lower left, upper right, and you get this kind of S curve in the middle. It's usually what it always looks like. All right, so the homework is on 234. It's all odds, so 1 through 5 odd. 9 through 11 odd.
So all of them are odd?
Yep. 15, 17 to 22, well that's even, 22 is an even. 23 to 25, that's odd. And 29 and 33. Yeah, so 17 through 22, that's odd. Okay, everything else is odd. Okay, if you need any graph paper, I've got some up here. There's 8 graphs per page. I don't think you'll need more than 1 page. Probably won't even need more than just the front of 1 page.